What you got there?
This is a good one. Picture two bullets, each exactly the same distance from the ground, each released at the exact same second, except one bullet is dropped to the ground, the other is fired from a gun. The classic physics thought experiment states that both bullets will hit the ground at the same time.
Based on what theory?
Based on the theory that the bullet that's fired from the gun has no wings on it, no lift. Thus, gravity has the same effect on it as it does on the drop bullet, and thus, they hit the ground simultaneously.
It's an age-old physics fable that says a bullet dropped and a bullet fired simultaneously from the same height will hit the ground at the same time. But it's so darn difficult to test that no one's tried until now.
So what's the plan?
Well, I've been thinking about this one for so long. While I have seen this experiment elucidated in textbooks the world over, I don't think that anyone, anywhere, has ever tried it full size, full scale, with real bullets coming out of real guns. That's what we should do.
It sounds like it could be kind of tricky, actually. I think we should do some shop experiments before we start using any live rounds.
Fair enough, let's start.
So before going ballistic with the ballistics, Adam comes up with a more simple way to put that textbook theory to the test.
Well, this test is going to be comprised of two separate parts, and I am using a bullet of sorts. You may recognize the steel ball bearing as some of our ammunition from Steam machine gun. Part the first. I'll be dropping this ball bearing from exactly table height, handily marked by this green line right here. I'll be filming its drop on a high-speed camera and counting how long it takes to get to the ground. Part the second. I'll be shooting this ball bearing from my little pinball shooter here, which I've marked out to be really accurate every time I shoot it, and I'm gonna fire it across the same grid and measure how long it takes to reach the floor on the same high-speed camera. If this myth is true, those two times should be identical. Okay, here we go. This is the drop from table height. In 3, 2, 1. Pretty simple.
Couldn't be simpler, but there's a lot more to this test than meets the eye.
Counting the frames of the high-speed shot, the marble took exactly 201 frames to get from my hand to the ground. And because we were filming at 500 frames per second, each frame is 2 milliseconds, which means that the total travel was 402 milliseconds. Or for those of you who love fractions, and come on, who doesn't? 4.02 tenths of a second.
So 402's the benchmark. Now, how will the fired ball stack up?
High speed ready?
Time for some pinball wizardry.
Here we go. Pinball shooter in 3, 2, 1.
And the results are flipping fabulous.
What do you got?
It's actually pretty cool. When I drop the ball from table height, it takes 402 milliseconds to reach the ground. When I shoot it from this pinball shooter, 410 milliseconds to reach the ground. It's 0.8% difference. That's pretty much identical.
With less than 1% difference, that's a pretty powerful result, and a provisional thumbs up for the myth. But Jamie's not impressed.
Okay, but I thought the story was about guns.
You really want to get to shooting guns?
Well, yeah.
Okay.
Bullet baloney or physics fact. This test is so hard, no one's ever dared try it. Does a bullet fired and a bullet dropped simultaneously from the same height hit the ground at the same time? Before breaking out the real bullets, Adam's letting loose with something a little more manageable. A paintball gun.
Perfect.
We've mounted this paintball gun so that not only is it perfectly level, but it's tuned back so that the paintballs will actually hit the ground before they hit the end of the shop. This should allow us to do some perfect comparisons between a fired projectile and a dropped projectile.
Which brings the MythBusters neatly to their next challenge.
If I fire a paintball gun from this gun and catch a shot of it on the high-speed camera at the other end of the shop hitting the ground, how do I know exactly when it left the gun? I'll tell you how. I've got a switch hooked up right here to the trigger of this gun. When I pull it, this battery powers an LED down there hooked up to our high-speed camera. All right, here we go.
So without further ado, Adam does the fire test. The high speed records the moment the light comes on, and the paintball hitting the ground,
Look at how beautiful that is.
making it possible to precisely time how long the journey from gun to ground takes, which, for this test, is exactly 555 milliseconds.
That is science.
Now, Adam gets ready for part 2 of the experiment.
So I'm just about to hold this paintball up at exactly the level of the barrel. I'm going to use a laser level to help me know it. Film it on high speed and time exactly how long it takes to get from my fingers to the ground. I will then compare that time to the fired paintball. Paintball drop test in 3, 2, 1.
This time, the difference between the fired and dropped paintball is 59 milliseconds. A lot more than the 8 millisecond gap between the fired and dropped ball bearing, which has the MythBusters scratching their heads.
Well, this is a conundrum. Our first 2 experiments seem to contradict each other. However, I think the culprit lies in the paintballs themselves. Watch this. See those trajectories? Each one's different. They're curving. That tells me that the irregular surfaces of the paintballs, manufacturing vagaries, is causing these things to have aerodynamic artifacts that makes them inaccurate, and thus, I think, renders the paintball test invalid. I don't see anywhere to go with this except to start using real bullets, and soon.
So far, testing whether a slug fired and a slug dropped simultaneously hit the ground at the same time
Oh, a little too powerful.
has been a mixed bag for Adam and Jamie.
Perfect.
In 2 small-scale tests, the myth was falling towards confirmed in one,
It's pretty much identical.
but busted in the other. So, what now?
We gotta go full scale with bullets, but dude, how difficult is that gonna be? I mean, for starters, I don't know how far a bullet fired level from a gun even goes.
Well, why don't we try a 45 caliber pistol? I mean, that has a large, slow-moving round.
And head out to the range and see where it hits the ground.
Exactly.
Perfect, let's do it.
And the shooting range is the perfect place to get the lowdown on launching bullets.
We're looking for a couple of different things here. The first is that we need to have all the bullets coming out of the gun consistently, so we know we're collecting accurate data.
That's perfect.
The second one is we're wanting to find out how they're dropping, how far away from the gun they travel before they hit the ground.
And before the boys blaze away, they're rigging the gun rigid and level, exactly 36 inches off the ground.
Nice, I think we're ready. The reason we've gone level is that I'm only interested in gravity's effect on the bullet once it leaves the gun. If I aim the gun higher, that bullet will go farther, but it's going farther because of its trajectory. If I shoot it level, then it starts dropping. Gravity starts having an effect the moment it leaves the barrel, and that's what I'm interested in. How fast does it drop, and how far does it go? Gun aside.
Right now, the guys have no idea where the bullet will land. So Adam and Jamie test to see how far the bullet falls over 100, 200, and 300 feet.
That one was half an inch above the other one. Let's go take a look.
Okay.
What we've got so far in terms of data is actually pretty freaking cool. This orange line represents the bullet at 100 feet. The laser sight was aimed just about an inch higher than that, which is just what we'd expect to see, a very little amount of drop-off. 200 feet, a little more drop-off. 300 feet, that blue line, a lot more drop-off.
Armed with that info, Adam and Jamie can now zero in on the drop zone, which they've calculated to be between 350 and 370 feet away.
Well, this right here is a runway. It's a runway for our little bullets to land on. I expect their landing to be rocky. I expect them to bounce. But most of all, I expect to be able to see where they land by the marks they make on this white paper. And hopefully, where they land is a reasonably discrete space.
Firing in 3, 2, 1.
Oh, that looks like we might have hit it.
And after letting loose one more time, Adam and Jamie discover the bullets are biting the dust roughly 360 feet from the gun.
I think we got what we came for. We've been able to predict fairly consistently where the bullets are hitting the ground. But the problem is we're outside, we could get a breeze that might kind of skew the results. And also, and this is the most important thing, the ground here is really uneven. So to go forward from here, we need a perfectly flat surface to work off of.
Well, all we need now is 400 feet of flat floor.
I think I might be able to handle that.
Once upon a time in the Wild West, a fired bullet could just about settle any bust-up.
All right. What?
But is it true that a bullet dropped and a bullet fired simultaneously will hit the ground at the same time?
That is science.
Out at the range,
All right, good to go.
Adam and Jamie found that a bullet from their .45 automatic flew 360 feet before it bit the dust.
I love this, man.
Now, all they need is a location to suit one of the most sophisticated experiments the MythBusters have ever attempted. And down by the shores of old San Francisco Bay, they've got one.
Ah, look at that. It's magnificent.
I love these old military buildings.
The historic 480-foot-long big event behemoth, Fort Mason Center.
Fort Mason Center is perfect for us for several reasons. At over 480 feet long, there's plenty of room for a fired bullet to come to rest. And because it's enclosed, there's no wind to worry about affecting our bullet. And then lastly, it's perfectly level.
So with the gun rest in place at one end of the room, Adam's first job is to make sure it's exactly 36 inches off the floor. And firing level.
I'm gonna fire a bullet to that target 20 feet away. Now, within that 20 feet, the bullet's not gonna drop at all. So as long as the bullet hole in that target is the exact same height off the ground as the barrel, I know I've got a perfectly level bullet.
Seating the gun rest. Firing in 3, 2, 1.
Dude, I'd say that is absolutely perfect, right on our laser line. That gun's firing level.
Works for me.
With the fired bullet rig sorted for now, Jamie rolls out the other half of the experiment.
This is my bullet drop rig, and the key component is this electromagnet right here, because it'll hold on to my bullet, and then on cue, it'll drop the bullet.
Okay, we've got all the sensors we need and all the equipment we need to time the exact amount of time it takes a bullet both to be dropped from 36 inches and to be fired from 36 inches off the ground. And we could simply compare those two times like we did with the paintball, but that's not good enough for us. For we have a bigger vision. We want to see that drop bullet hit the ground in the spot the fired bullet will be skipping off. That's what we're about to set up.
That's right, folks. This time, both halves of the experiment are going to happen at the same time. But it also creates a humdinger of a problem. How are our son-of-a-gun scientists going to release a fired bullet and a drop bullet at precisely the same moment?
Let me set up this experiment for you. Do you see the little red light in the lower left part of the frame of this high-speed shot? That's an LED coupled to the electromagnet holding this bullet up in the air. Now, the moment that LED goes off, I know that the electromagnet is no longer powered and it's dropping the bullet. Now, see the tip of this gun? The moment I see a bullet peek out of that, that's when I want the electromagnet to go off. So now, look at the high-speed shot again. You'll see I can see the red light, I can see the electromagnet, I can see when a bullet leaves the barrel, and I can make sure they all happen at precisely the same time.
So before rolling the drop rig 360 feet down the room, the boys just want to make sure their little synchronizing system is going to work.
Simultaneous firing and bullet drop test in 3, 2, 1.
Let's see how it looked on high speed.
Where the MythBusters quickly discover they have a problem.
Let's look back at the timing about when the light goes off.
While the gun and the timing LED go off together, The dropped bullet decides to delay its journey south.
It sits on that electromagnet for a while.
Yeah.
Do you think there's any residual magnetism or something like that? If you look at this high-speed shot of the bullet on the electromagnet, you'll notice it hangs out for 65 milliseconds. That tells me there's a lot of residual magnetism in the electromagnet itself, even though it's turned off, and it's no good as a mechanism for our drop. We've got to rebuild a mechanism, and we've got to rebuild it fast. Here we go!
MythBusters and world firsts go together like ham and eggs. There's the Pykrete boat.
I'm king of the world!
Breaking glass. And the lead balloon.
You know, if someone says it's impossible, we just take it as a challenge.
Now, the MythBusters are testing a real doozy.
Everything's hot, ready to go.
Bullet shot versus bullet dropped. But a malingering magnet is holding up the show.
As soon as it's released, it's just staying there.
But do you think Adam's going to let something like that stand in his way?
Awesome, that works.
Oh no.
So, the electromagnetic is gone. It's on the scrap heap. We've got a new little solenoid in there which will whoop, get out of the way and let the bullet drop. All we got to do is try it once, get our timings right, confirm them, and we should be ready to do this test.
So the new simultaneous release system is ready for a test fire.
All right, simultaneous release in 3, 2, 1.
All right, let's see how it did on high speed.
But once again, there's a timing problem.
Solenoid's way too slow.
Yep.
It's not letting go.
The most difficult thing about this whole experiment is getting the fired bullet and the dropped bullet to become airborne at exactly the same time. And when you realize all the stuff that is going on here, it's trickier than you might think. I mean, the gun has to do its thing, the release mechanism has to do its thing, and we can't tolerate even a few milliseconds of variation in this mix to make the result that we want to see happen. It's hard.
Now there's an understatement. So cue the brainstorm.
We're not even seeing the pin start to move.
It gave us the problem that we currently have, which is that it's late. Make it hot again.
Having spent the past 4 hours trying to sort out the solenoid,
Look, let's do this twice.
the boys are now staring failure square in the face.
And all it is about figuring out some way to mechanically push between these two.
Until Jamie snatches victory from the jaws of defeat.
If you have a hinge that you pull in the middle,
Yeah, that's what I
there needs to be some sort of a little bitty catch that is on its edge. I could make a clip like that.
He adds a small metal clip to the trigger to delay the gun the minuscule milliseconds needed to match the solenoid.
Everything's hot, let's do it.
And after a few test fires and a bit of fine-tuning, it works.
Bullet leads to the gun. Oh, it's good. It's good. It's 1/3 of a millisecond difference.
Wow.
That's freaking perfect. Let's go do this full scale.
Okay.
Which means rolling up the room 360 feet to stake out a drop zone.
Right about there. That's where they were landing out in the shooting range, so this is where I expect them to land here.
Okay.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
Let me walk you through our complicated experimental setup here. It all starts when Jamie tugs on this string, which will pull this clip right here, made out of steel, out of the way. That clip will allow this spring to do its work. The work it wants to do is to pull this metal finger towards the trigger, pulling the trigger of the gun and setting this bullet off on a journey down this way. But that's not all that it's doing. Oh no, come back. Because at the same time that it pulls the trigger to fire this bullet, it is also connecting to this wire, which is going to a computer, which is going all the way down here. Let's go. Aren't you glad we're speeding this part up? So, simultaneous with the signal that sends that bullet from the barrel of that gun, an electronic signal sends this bullet falling from our little drop rig so that hopefully when it reaches this point, it will meet its friend, the fired bullet, and all of it will be captured on that high-speed camera right there. All right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet dropped versus fired. In 3, 2, 1.
Adam's hoping this time that the bullet is as well placed as Jamie's optimism. But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Ugh. I can't wait to see the high speed. So, dude, this bullet carved a streak right under the drop zone. I think this might be the shot we've been looking for.
In real time, it's impossible to tell what happened until Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the MythBusters can claim a world first for themselves and a victory for physics.
Let me put 39.6 milliseconds into some perspective for you. When you go to the movies and watch a projected celluloid film on the screen, you know that that film's made up of individual images, right? What you might not have known is that it takes 24 of those per second to make up the film that you're watching. So each one is on screen for exactly 1/24th of a second, but you don't notice that because it's faster than your eye can register. Well, that 1/24th of a second is actually longer than 39.6 milliseconds. That's how close those two bullets were.
2 bullets, 1 dropped, 1 fired. Amazingly, they ended up in the same place at the same time.
Dude, this myth was every bit as much fun to test as I was hoping it would be. And I gotta say, even though the physics textbooks had it right, I love the fact that we did it full size with real unmodified bullets. I bet no one has ever tried that before.
I think you're right. And whether it was ball bearings or bullets dropped or fired, they all hit the ground at the same time.
Yep. Gravity, man. It's not just a good idea, it's the law. Confirmed.
Confirmed.